Thanks very much, Rachel, and thanks, guys, for having me, and also thank you, Zoe Turner, for sort of initially putting me in touch and inviting me. So yeah, my name is Hugh Day. I'm a maths PhD student at the University of Bristol. I also co-organise the Jean Golding Institute's Data Ethics Club, which is a online reading group and discussion group where we discuss all things data ethics, and that's how Zoe and I know each other. And at the end of the talk, I'll include some information about how you guys can get involved in that if you're interested in joining as well. I'll also see some of you at that conference in July. I believe myself and two of the other co-organisers are speaking at that conference, including myself. I've done some work with the digital health group here in Bristol, so perhaps some of you will find some of the work I've done quite interesting. But yeah, so a bit about what I'm going to be doing today. So I've been doing quite a lot of outreach work in schools, and I remember when I was kind of 16, 17, I found statistics really boring, and when I was kind of given the opportunity to do this outreach work, I wanted to find a way of engaging students both in sort of data science in general, but also thinking sort of about data ethics. And so I've had a few discussions with Zoe and Rachel about how could I talk to you guys about the kind of work that I do. And so initially I had the idea of just sort of give a commentary on what I do. And Zoe actually had the suggestion that I just give you guys the outreach talk. So in a minute, I'm going to start sharing my slides. And I'm aware that a lot of people in here are professional data analysts and data scientists. So I hope you don't feel patronized when I ask you questions that I'd usually ask towards like sixth form students who are just studying statistics for the first time. But the kind of the general idea of the talk is that I teach them basic linear modeling, and then I get them to design an algorithm for hiring and firing teachers. And I kind of use the dread on the teachers' faces to fuel participation from the students, and it usually works pretty well. So today I'm going to give you guys hopefully a refresher for many of you, but if you're not familiar, kind of a crash course in basic linear modeling. And then we're going to take a little spin on it, and we're going to design an algorithm for basically evaluating our bosses and then deciding whether or not they should be hired or fired accordingly. So I'm going to start sharing my screen. So hopefully, can you see this all right, Rachel?
Yeah, that's great.
Happy days. Yeah, so the talk is entitled "Weapons of Mass Destruction." It's inspired by the book of the same name by Cathy O'Neil. So I'm going to start by reading a short passage from the book, which sort of sets the stage. So in 2007, Washington, D.C.'s new mayor, Adrian Fenty, was determined to turn around the city's underperforming schools. He had his work cut out for him. At the time, barely 1 out of every 2 high school students was surviving to graduation after 9th grade, and only 8% of 8th graders were performing at grade level in maths. Fenty hired an education reformer named Michelle Rhee to fill a powerful new post, Chancellor of Washington Schools. The going theory was that the students weren't learning enough because their teachers weren't doing a good job. So in 2009, Rhee implemented a plan to weed out the low-performing teachers. This is the trend in troubled school districts around the country. This is in the US. And from a systems engineering perspective, the thinking made sense. Evaluate the teachers, get rid of the worst ones, and place the best ones where they can do the most good. In the language of data scientists, this optimizes the school system, presumably ensuring better results for the kids. Except for bad teachers, who could argue with that? Rhee developed a teacher assessment tool called Impact, and at the end of the 2009-10 school year, the district fired all the teachers whose scores put them in the bottom 2%. At the end of the following year, another 5%, or 206 teachers, were booted out. So that kind of sets the scene. So what we're going to be doing today is we're going to be looking at the basics of like linear regression and correlation. So we're going to look at a couple of scatter plots first and get some ideas about like correlation coefficients and some other ideas that come into play when we represent data. And then from there, we're going to generalize it and then start using these models predictively. So the first scatter plot, originally I was just going to do the heights and weights of bond actors, but it's kind of quite a heterogeneous group of similar people. So I've included Judi Dench for some variety here to spread the data set out a little bit. But it'd be quite a common question, and maybe like a GCSE maths exam to draw a line of best fit for this scatter plot, right? We've got on the x-axis we've got their height, on the y-axis we've got their weight. And lots of students would be familiar with drawing this, but some of them might be surprised to find out that you can actually get a mathematically sort of rigorous way of doing this as well as you can, right? And so some of you might be familiar with like a product moment correlation coefficient, or PMCC for short. And one thing I try and do in outreach talks is I found that the more equations you show, the less people pay attention. So We're not even going to worry about the equation today. We're just going to try and get an intuition as to how this kind of value works. So it's denoted by the lowercase letter r, and it's a value between plus and minus 1. If r is positive, that implies positive linear correlation. So an up and to the right straight line would be a good fit. If r is less than 0, that implies a negative linear correlation. So a downward sloping line is a good fit. And if r is close to 0, that implies little observable correlation, at least for a linear model. So Rachel, if you wouldn't mind sharing the first question on Menti. So what I usually do when I have students in classrooms, I get them to stick their thumb out in front of them and then basically say, if they think it's +1, they're going to point their thumb to the ceiling. If they think the correlation coefficient is like -1, they point down to floor, and then sort of sideways for anywhere in between. But unfortunately, we're online today, so if you could have a vote and humor me, what do you think the correlation coefficient for this data might be?
So obviously I am getting some answers in.
Yeah, just read some out.
Okay, I shall do that. So we're starting off with 0.65, and then we're just saying there's a few +1s at 0.8, 0.6. We've got 0.75. We've got 0.1 to 0.3 ish. Lots of +1s, 0.85, 0.75. You're making them think today, and they're enjoying the invitation for you to make them think.
Awesome.
So yeah.
So whoever said
you get the picture.
Whoever said 0.75 was the closest. So it transpires for this data set the correlation coefficient is 0.76. So we kind of everyone said positive numbers, which is kind of reassuring. So we see in general that you'd expect a positive correlation between heights and weights of people. And in this case, we've gotten in this case Excel, but you could get any kind of coding language you're more familiar with, like R or Python or something like that, to draw a nice straight line of best fit from here. And so what we're doing with these kind of data science tools is that oftentimes when we get presented with lots of information, we actually we can't use it as easily. And so we're using these tools to essentially zoom in on the data. And so instead of me just giving you a list of values or even showing you a plot, I can just say, well, these are these variables and this is the correlation coefficient between them. And immediately you have some understanding of like, okay, well, there's a quite a strong positive linear correlation between these two variables. Okay. So the next one is a data set I've made all by myself. And so on the x-axis, we have the time spent playing video games per week, measured in hours. And this is in a household. And on the y-axis, we have the number of police visits per year in a household. This is this one always provokes strong emotions from sixth formers when I share this one. But could I get I think the next question for me, Rachel, which is what is the correlation coefficient for this graph?
Yes, I've shared that one too.
Cool, and feel free to start reading out any values that people want.
We've got lots of ones. We've got a 0, either zeros or ones, predominantly ones with a 0.9.
Okay, good stuff. So in this case, whoops. There we go. Cool. Technical difficulties averted. So in this case, the correlation coefficient is exactly 1. So like a fact from kind of high school geometry is that having 2 points in like 2D space is enough to completely determine a straight line. And so what that means is if I want to draw a line of best fit and I have exactly 2 data points, then I can always draw a perfect line of best fit, which goes exactly through these 2 points. As soon as I add a third point, it could be that my line of best fit doesn't go through every single point. And because the correlation coefficient is in some sense capturing how good does my straight line of best fit go through my data points, we can see in this case that my correlation coefficient is perfect. So that being said, the next question for you guys is requires words, I'm afraid, but why is it problematic to draw conclusions from this data?
People have got to think now, so you have to give them a bit longer here.
That's okay.
I know you know the answers.
Yeah. No.
But we are going to be getting some responses, so people are saying there's not enough data points. That's predominant answer.
Yep.
Need more data. sample size is too small,
Yeah.
etc., etc. All
Yeah.
saying the same thing.
Yeah, exactly. So so there's this idea of like fragility of data, and so if we think about like the blonde actors example, imagine I was let's say I was entering data, or even I just had some anomalies in data, but let's say I was entering data and I got Roger Moore and Judi Dench mixed up and I got their heights the wrong way around, and so two of these data points, I'm not sure which one Roger Moore is, but this one and one of the ones over here get switched around by accident. Then in that case, my correlation coefficient would probably decrease, but it would still be in the realms of kind of 0.7 maybe. Okay. And so whether there's a mistake in data entry or even if there's like an anomaly, we still kind of see this. We see that the patterns that I'm capturing with, in this case with my correlation coefficient, are still captured to some extent. You can imagine a situation where if these two were entered the wrong way around, or if I just happened to sample two different people which had the other way around, then my correlation coefficient now goes from +1 to -1, right? If this point was up here and this point was down here, so if the left point was up and the right point was lower, then I'd have R equal to -1. And that would completely reverse the relationship. And you could draw completely different conclusions from that. So the other question I'd ask is, say if we had a larger sample size which showed a similar pattern, we had a generally more robust, less fragile data set. What's problematic about concluding that there's correlation between time spent playing video games and criminal behavior? So what kind of answers are we getting through, if any?
That was my bad. I don't think I moved it on enough. So we're looking at. So what was the question? Just to double check.
So we're on slide 7.
Okay.
With more robust data, what is problematic about concluding that there is correlation between time spent playing video games and criminal behavior?
Okay. So this is now we've got more data. Okay. So some of the responses are you're looking at potentially correlation, not causation. It's too big of an assumption still. Are they related? It's the same kind of thing. Other factors present but not in the data.
Yep.
That kind of thing.
Yeah, all great answers. So the one thing I did there that was pretty cheeky of me is I said criminal behavior, right? And the y-axis variable is not criminal behavior, right? It's number of police visits per year. I'm sure you guys can think of plenty of examples where you've interacted with police, and it's not because you committed a crime, right? Maybe you witnessed a crime, maybe like you're in a car accident that wasn't your fault. I'm starting to sound like an insurance ad, but you get the idea, right? And so what I did there is I sort of I used a proxy variable where I kind of approximated criminal behavior with police visits per year, right? Like if one of your neighbors had policemen coming over like every other weekend, then maybe you'd start getting like a little bit suspicious, like, oh, what's going on here? But you're absolutely right. There's not enough in this data to necessarily make that conclusion. And so this is a great example to use with like A-level students because lots of them are used to this sort of narrative being pushed of like video games being correlated with violence and things like that. And it really winds them up and it gets them thinking like, why would I want to challenge these assumptions? So one thing that we'll see later on is that we'll be forced into circumstance where we want to try and like approximate a certain value and we can't actually measure it, so we have to use a proxy variable in its place. Okay. So the next graph we're looking at, I really like this graph. So we're looking at on the x-axis is percentage of people wearing seatbelts in the US per decade, and to be completely explicit, that's people wearing seatbelts in cars which are not in outer space. And on the y-axis we have astronaut deaths per decade, and again to be completely clear on that, that's astronaut deaths on mission. Not in cars, but in space, right? So I think slide 8, we should have a question as what is the correlation coefficient for this data?
Okay, I have moved it on now, so we're looking at slide 8, and we are getting 0, 0, 0, minus 0.6, minus 0.2, minus 0.25, 0, lots of minuses or zeros to different degrees.
Fair enough.
Yep.
So the negative trend is right. We had, I think someone said minus 0.6, so that guy gets a gold lucky star. Yeah, so in this case, we're seeing negative 0.6, right? And perhaps some of you said 0, partly because the data looks sort of a bit flat, even though it's a general trend sort of downwards and to the right. But you'd also perhaps suspect, why on earth would these two variables be related, right? And that's an interesting thing to think about. So I think the next question on slide 9 should be, why do you think these two variables are so strongly correlated? What do they both have in common? And so just for comparison, we saw that height and weight, which we sort of universally agree have some fairly strong correlation, had a coefficient of about 0.76. So in terms of magnitude, we're not that far off. So in some senses, this correlation should be quite compelling. So do people have any thoughts about why these two variables are so strongly correlated?
So a couple of responses so far. Safety is what is in common. Common causes technological advancement, carelessness in common, health and safety legislation, advances in health and safety, so changes over the time in health and safety.
Exactly right. So the key thing there was that both variables have some sort of relationship with time, right? You think the way I sort of provoke this thinking with students is I say, okay, well, we'll think about when your parents were kids. Do you think they had to wear seatbelts as strictly as when you're now in the car with your parents? And most of them would say, no, I expect my parents wore seatbelts less than me. So over time, we are seeing more people wear seatbelts, and then because of safety standards and technology advances and things like that, we're seeing less astronaut deaths on missions typically. And so we see that there's actually a hidden proxy variable with these two with these two variables, and it's time. And so sometimes we can so that really illustrates sort of the power of proxy variables, is sometimes you see two variables that you don't think should have a relationship, and they turn out that they do. There's a really interesting website called Spurious Correlations, which I'm sure some of you are familiar with, but it has a lot of interesting examples of two variables that definitely shouldn't be correlated. I believe there was one that was sort of it was cheese consumption in Ohio versus the number of deaths where people accidentally suffocated inside their own bed sheets in the US, and they were very strongly correlated. But even in that case, it wasn't apparent that there's a proxy variable involved. But sometimes in cases like this, there is some causation apparent from the inherent correlation. So last graph I promised that I'll show you. So over Christmas, I conducted an experiment of questionable ethics. So I went around various family members and I asked them how quickly they could run 100 meters. I have a baby cousin who's just turned 1. So I asked the cousin's mum how quickly they think their child could traverse 100 meters if push came to shove. And I also asked Grandpa how fast he thinks he could do it, with the Zimmer frame if necessary. So this is the graph I got. So on the x-axis we have age in years, on the y-axis we have the time to run, or at least traverse 100 meters in seconds. So I think the next question should be for slide 10, what's the correlation coefficient for this data?
I've moved it on. Let's see what people are saying. So I've got lots of zeros so far. Now we've got a little bit more of a positive one. 0.8, 0.05, 000, or not, so non-linear.
Right.
Yeah, that's predominantly what people think about this
data,
Hugh.
Yeah, I'm really glad that there was the non-linear answer there. So the answer's very sort of, it's close to 0, is 0.24 in this case. And I think the point that someone made about being non-linear is super important. I have kind of for the purpose of this talk, shoehorned and just assumed that everything I show you has a linear relationship, which is obviously not, frequently not the case. And so you could imagine a circumstance where you might consider a higher order polynomial, like an x squared type curve to model this sort of data. Or you could even imagine a scenario where you split the data in half, say around like 2025, and then you did one maybe like exponential decay for the left-hand side of the graph, and then maybe an exponential growth for the right-hand side of the graph. Let's stay in my kind of, I've shoehorned us into this situation of using linear models, but let's take a think about what could we do to make this model better, right? So one thing we could do is we could consider other variables. We could consider what else is a good predictor of how fast someone runs 100 meters. So I think the next question should be for slide 11 is, I've sort of answered it, but I guess how can we model this data better? Terry, is it okay if you just skip that question and just go straight to what other variables could we introduce to better predict running time? And let me know what people have to say.
Muted, aren't I? I'm actually talking sense for once, and I was muted.
Oh, I was just there like, oh.
Where's she gone?
Yeah.
Yeah. Okay. So there's a few answers here. So some variables might be gender, BMI, lung capacity, leg length, ability, muscle strength.
Nice.
So some lots of physical attributes, fitness, etc., etc.
Yeah, all good ideas. Perhaps you could consider if someone has lots of injuries, that could affect even if they're otherwise in very good shape, and things like that. And so what we could do is we could consider a more general linear model, which might be familiar if you're sort of a statistician or a data scientist, where you have an output that you're essentially trying to predict, and then you want to see what other inputs can you use to predict these. So one thing that I'm familiar with is using this in the context of health scores. So if you're familiar with national early warning scores, then you take in 5 or 6 vital variables, and you use a kind of weighted linear model to try and figure out how healthy someone is based on their heart rate and blood pressure and respiratory rate and other things like this, Glasgow Coma Score, etc. But when you do that, especially in the context we're in, where we're trying to develop the model, we need to be quite wary of introducing more variables. So the next question for slide 11 should be, what drawbacks do we have of introducing more variables? So I'm curious if anyone has any thoughts on this. So
I don't think we haven't really got a slide for that, so it might be just
it's on slide 11. What drawbacks do we have? So it should be, hopefully there's another question, but
yeah, I'm not sure. I don't think we actually reflected that in okay, I didn't do it.
It's got both. It says include. What would we include and what drawbacks? It's the same one. So I think if it's
a sub question,
yeah.
Okay, so
keep going on this side. So
yeah.
I didn't do it. I am perfect after all.
So were there any thoughts from anyone on feel free to unmute if you wanted to contribute that way, but on drawbacks?
Okay, so a couple of things people have said are overfitting the data, so confounders, complex to visualize, more strenuous data collection, might find correlations that aren't causes, hard to determine what the relationships are if you introduce more variables and so on. Again, I think there's sort of similar theme as to more variables, more complicated, and too many assumptions being made.
Yeah, for sure. No, all great answers. So the overfitting one is a really common problem, and also the visualization one is a huge pain in the neck when you're trying to do something that's very visual in nature, like if you do sort of unsupervised clustering, for example. Yeah, absolutely right. And so what we want to make sure that we have enough data, and our data probably wants to scale some way with the number of variables. So in this case, you could make a pretty strong argument that even with one predictor variable, just age, I don't have enough data points really. And maybe you'd want for every age, you'd want maybe for every 5 years, maybe you'd want 3 people, just as a rough benchmark. And then you think, well, okay, say let's add, someone suggested BMI as a potential second variable. Well, now you want to think, okay, well, for each age and for each BMI, maybe you'd want to think, well, okay, actually, like how do these 3 different interact? So maybe for every age, you have 3 different BMIs, just for example. And so this all starts scaling up quite quickly. And 3 is just an arbitrary choice there. Oftentimes, we don't get to make the decision about what data we're presented with. We're just given a population. We just have to sample accordingly. But we can see that whilst perhaps our predictions would be stronger. In theory, in practice, things often get a lot more complicated. So that's my my crash course on correlation and linear models. And so for our purposes today, what we're going to be doing in the next slide is looking at building our own model. So this is obviously set up for my school outreach things. Instead of designing our teacher hire fire algorithm, we're going to be I'm not claiming that anyone's going to lose their jobs over today's discussions, but we're going to be evaluating our bosses instead of our teachers, right? So the first question, which should be for slide 12, is what makes a good boss? So take off your data science caps for a second and just share some what makes a good boss, just attributes and things like that. When I work with kids, I mean, I have to discourage them from naming names. I guess maybe I should make that same discouragement to you, but I feel like everyone's
no.
Oh no,
go for it, guys.
Yeah, okay,
Hugh,
yeah, just
Hugh, can I just ask a question on the data before, as people are probably thinking about this? There were 2 points, and one of the things that we tend to do as well is remove the outliers.
Yeah.
And so the outliers in this case is grandpa and young cousin.
Yeah.
That wasn't part of the model, but that changes things, doesn't it? So do you have any views on outliers and what we do with them? And
yeah, it's such an interesting thing, right? Because sometimes we're so we're often very keen to say, well, this doesn't fit our pattern, so maybe the data's wrong, so we need to remove this thing. And so in the same way that, you know, when we were worried about overfitting, we almost have this thing where we're now so focused on the pattern that we want to see that we'll sort of sometimes we end up removing data points, outliers, to those ends. And there are frequent times when that's the correct decision. But I think equally, the more time you spend curating your data to make it fit your conclusions, the more skeptical you should be of those conclusions that you draw. So for example, like when I suggested you could split the data in half, right, say at like 25 years, right? I like to think I'm in my athletic prime now, or maybe 20 years, maybe 5 years ago was where I was at. But in that case, if I just looked at the first couple of data points from baby cousin all the way up to Hugh at 25 years, then an exponential decay, for example, would fit quite well there, and removing the baby cousin wouldn't be necessary. And so, yeah, I guess my thoughts on that are it depends on a case-by-case basis. But the more that you have to do to your data to make it fit your conclusions, the more skeptical you should be of those conclusions, at least in my opinion. Does that sort of answer your question, Zoe?
It does, thank you.
No worries. Yeah, so the plan is hopefully I don't know if Rachel's if you shared the question yet, but what makes a good boss? Do people have any thoughts on this?
We do have thoughts, so I'll read some of those out. So the first two say supportive, motivational, their experience, their expertise, which they share, frequency of meetings with them, qualifications, high level of team productivity, years of experience, understanding, positive attitude, clear direction, empathy, low staff turnover. These are some really good things, actually.
Nice. Actually, I'm gonna stop screen sharing on my end, and can you screen share so that I can see? Is that right?
Yeah. So it's a good job I didn't make all that up. So here we go. That'd be really embarrassing.
Yeah.
So I'll just share my screen, and I'll just find out where that is. One of the windows. Let's go for here. So as I just said, without making it up, supportive.
Nice. Lead with direction, understand overall strategy, want to coach team, don't micromanage, set objectives, empathy, enthusiasm, knowledge of the area. How often do they bring in cake? Fantastic variable. Absolutely will be including that in my model for the future. That's great. One. Yeah.
Output, happiness of staff.
Fantastic.
Yeah, some good suggestions.
Yeah, some really good suggestions. Okay, so now everyone's got to put their data science caps back on. So I believe for the next question,
I think it's contained in one. So in the same question, we kind of said, if you read the question out, that people can put their answers on this same question. I think they can input onto this same question. So if you read out the next part of that question, which I think is about variables, or
yeah. So there's some of these where it's clearly measurable. You can measure how often your boss brings in cake. You can measure staff turnover. But for example, when you think about like how supportive someone is, or happiness of staff, that in some ways can be more difficult to measure. So think for the things that have been suggested here, what proxy variables might you use? So the thing I get students to think about when we're building this teacher firing model in class is to think not just how you can measure certain aspects, but also what data is actually readily available. So for example, if you thought like a good teacher would be empathetic, you hand out emotional quotient tests to all your teachers, but they're a little busy at the moment doing all the other marking that you had them doing. So you got to think about, okay, what data do I already have? Maybe I have like their grades, the attendance, grade improvement over a year, number of complaints, their qualifications, things like that. So think about what data is collected about you as employees, and then also about your boss that's there and present already. And then think of those variables. What proxies can you use to sort of approximate your boss being good or bad? And for each one of those, think about what kind of like correlation coefficient you'd have. So I guess more cake is better. So you'd maybe have frequency of cake would have a correlation coefficient with how good of a boss is, with like, I don't know, 0.6, for example. If you thought it was good, but it's not, if your boss only brought in cake and did nothing else, then it wouldn't be like amazing. So hopefully that's clear. So let's see.
So I've moved the page down, so it's sort of moving into people's ideas on how to measure and what that correlation might be.
Yeah, so we've got happiness of staff measured by staff surveys, positive correlation with satisfaction.
360 reviews, if you're familiar with those.
Hugh. I'm not familiar with those. What are those?
It's when somebody is, I'll get this wrong now, of course, sort of assessed by lots of different people. So you get different, it's effectively being surveyed by different people. So you get different perspectives on a person's sort of, also behavior, not behavior. It's a very rounded review of individuals.
Fair enough. Yeah, and that's if that's readily available, that's even better. Happiness of staff measured by staff surveys. Turnover rate has negative correlation. Completely agree. And then you can also think about output, right? And I think that's a really interesting one. So maybe whether or not you're working in the NHS, but if you're just working for any given company, one thing that would be important is how much profit does your department make? And so maybe you'd kind of think about, okay, well, who's in charge of that department? So how much profit are they sort of overall responsible for? But as soon as you start thinking about those kinds of things, you end up with a problem where we have to consider, are there circumstances that exist where your measured variable, so your profit, is high and the boss is still bad at their job? So is there a case where a boss is terrible and they have a really good team by chance? And in cases like that, the boss would stay in their position because this evaluating algorithm would say that they're good at their job. Similarly, like I know the cake one was kind of a joke. I mean, it's a great idea.
No joke, Hugh. No joke.
No, I know. We take cake very seriously at Bristol Maths Department. Don't worry. But you can think of an example of a boss who literally does nothing, but they do bring in cake every week, and it's like, okay, well, they're objectively a bad boss, but like they do bring in cake.
And it could be that a team, a boss isn't very good, isn't very effective for various sort of things mentioned here, but and because of that, the team has to be really good. The team themselves have to compensate. So people are picking up on here on the things where the data exists. So if you were to just use the data and where it exists, these are probably the things that you could measure, as opposed to the measuring empathy, measuring how happy they made you feel and things like that.
So I think the length of one-to-one meetings is a really interesting one, because I guess everyone could agree that if I had a boss who I got to see for 5 minutes once a month, you'd argue they're probably not very good at their job. But you could also imagine a situation where there was a boss who existed on a 2-hour meeting every week. or even, you know, with higher frequency, so like an hour meeting every day or something ridiculous like that, and they were overly micromanaging you. And so in that circumstance, you'd actually equate that with them being like a worse boss. And so in that case, you'd maybe think, well, maybe a linear model isn't the right thing here. Maybe I want like a quadratic model with kind of a bump in the middle where, I don't know, depending on your personal preference as well, which is a really important thing. But if you're just starting out, maybe you need more feedback from a boss. And if you're kind of more experienced, you can just kind of your boss's more hands-off approach. And I think this is also an interesting one, and it applies to the teacher one as well. Like, actually, you need to think about what kind of boss is someone, and so like how different people have different like leadership or indeed teaching styles. And so making this sort of evaluative measure as just a raw numerical output can lead into problems, because what I've asked you guys is, what do you think makes a good boss? And so if we were to design a system that outputs like a rating score for each boss based on these metrics, then it would be, what does this NHS analytics community think makes a good boss? And so hopefully you guys who have bosses who you think are good would be scored highly by your algorithm, but there could be bosses out there that are also good and potentially good in different contexts and different industries, for example, or with different sized teams, and they would be ranked lower by the system. Okay, so that's great. If I could, am I okay to take the reins and go back to screen sharing?
Sure.
Cool. I've forgotten how to do that. I always forget the prompt from current slide. Okay, so can you guys see my screen again? Okay.
Yeah.
Good. Okay, so let's think about conclusions. So one thing, and whether or not this is obvious to you guys, but thinking about are we removing bias by getting sort of an automated decision-making system to do it for us? Some people have this sort of feeling of, well, if a computer's doing it, then it's a sort of unbiased approach. But in this case, what we've done, as I've just said, is that we've actually just sat down and just encoded our bias. So we're saying the higher the frequency of cake that they bring into the office, the better they are as a boss. And that's our bias. We really like cake, and so we think that's a really important aspect. And, you know, for example, say if I'm a kind of person who really likes a lot of hands-on supervision, then I'm going to say it's really important that I have a lot of contact time with my boss. And so my personal model might really highly value that personal contact time. Whereas if you're a more independent worker and actually need a bit more hands-off approach, then your boss, who might work really well with you because they just let you get on with stuff, would be sort of poorly ranked by my system, right? The sample sizes one is particularly relevant in schools, so you can imagine certain variables where we don't have many much to measure, depending on the size of your team. If you know, for example, if you're in a smaller team, like let's say even like a team of 20 or something, and you had one boss, you need to think like if that boss was antagonistic towards a small group of that team, then is 5 reviews enough for your model to penalize this person? Should it be enough for HR to go, actually you're being discriminatory or whatever towards this group of people, you're not doing your job well enough by making people more welcome? And as we discussed, the larger number of variables you have, the wider, the sort of the denser you want your space to be. This is sometimes referred to as like the curse of dimensionality in sort of data science and machine learning disciplines. But yeah, essentially the idea that the more features that you care about, the sort of denser you want your feature space to be, right? I talked again about optimizing for proxies. So we can have a situation where we just have like I said, like if a boss works out that they might keep their job as long as they have really long meetings with everyone, they might just force really long, boring, the classic, this could have been an email kind of meeting. They could just force lots of those. And And then, and this was quite relevant with the school hiring and firing algorithm. But you could imagine if you were a boss and you were being evaluated. Imagine if someone came up to you and said, "Well, this algorithm says you're not very good at your job, so you're on notice, or even you're going to be fired." Thankfully, in the UK, we got some sort of GDPR, data protection type laws that give us a little bit more agency when there's automated decision making being made about whether or not we could keep our jobs. With the example where we're looking at running, it's pretty easy for me to I can make a model, and then I can just go and ask someone to go run 100 meters, and then I can just check, and I can just compare it with this line, and if they're off this line, then there's something wrong with my model, right? My model is this line, and so I've got to think, okay, well, what about this person was not accounted for in my model? In this case, it could just be my sample size is so low, or I've just assumed it's linear in this case, and it's just not. But even as I build more sophisticated models, because I have an output that I can actually compare it to, it's a lot easier to see if I'm off the mark. In this case, because we're making something that's evaluative, there's not really like a target, right? It's not objective if someone's there will be occasions where someone is clearly a good boss and where someone's clearly a bad boss, but often it's quite subjective to personal preference. And in particular, if you're the boss being evaluated, of course, you're going to say you think you're a good boss. And so you giving feedback isn't really going to be looped in there. And so there's a lack of a feedback loop in that system. And that's why we need to always be careful when we're doing something evaluative, whether it's evaluating teachers or bosses or even like health scoring systems, right? We need to have some kind of feedback loop built in that's separate from the model itself and as objective as we can make it. Okay. And then the last point I sort of wanted to mention of what could go wrong here is that it's sometimes difficult, as we've seen already, to look at links between predictor variables and outputs. This is an interesting graph. And I think this is slide 14, Rachel. There's should be a Menti question. That's what happened in second year. So this is my my undergraduate grades. I wasn't able to go outside and touch a lot of grass as an undergraduate, but I did decent in my studies. You see, I did very good in first year. There was a dip in second year, and then things kind of improved third and fourth year. So I'd be super curious to wonder if you guys would be able to explain what happened in second year. What caused the dip?
I've put that question up, so if people want to, I think you can respond to it. Does it look normal? If anybody's going to, I can see the question. I can't quite. Yes. Oh, I did it as a word cloud. Yeah, that was it. It was. I did it in a different way, and I confused myself. Is what precisely happened right then. So what we've got is. Shall I share my screen? Let's just share my screen because it looks fun. It looks fun. There you go. This is what happened to you in your second year. Do you agree with any of that?
Harder modules, too much partying, boozing with friends, pandemic. Yeah, okay. So the correct answer is on there. If I can reshare
okay.
My screen. Yeah, so the correct answer is I got a girlfriend right before exams, and that was 2 people had got that correct. So well done. But yeah, the point was that the explainability of data is often very difficult just on what you're given. Yeah, I also use this as like a warning to A-level students to be like, hey, just like do exams, like yeah, do good, revise. But yeah, so I think that's kind of all I really want to say. So this slide was hastily thrown together whilst people were joining in, so I apologize if it looks like I've copied and pasted that book cover off Google Images. It's because I have. But hopefully you found today interesting, if a little bit unorthodox. So I was sort of inspired by Cathy O'Neil's work, Weapons of Math Destruction. It's probably my favorite book on this kind of topic, and it's a really nice introduction to these kind of ideas. As I said, I help organize the Gene Golding Institute's Data Ethics Club. So if you're interested in getting involved, we have a website, dataethicsclub.com, and we're also on Twitter, which I help manage the Twitter accounts. If you're interested, that might be a good place to look. Yeah.
Okay.
Kind of what I have to say.
That's really enjoyed that, Hugh. That was fantastic. It was just what we hoped, wasn't it, Zoe? It was just what we hoped for.
Was brilliant. And can I just add, for the purposes of the people here who are from the public sector, if you want to join a reading group, they're going to be doing this book, going through it, Weapon of Mass Destruction, on the 17th of May at 12 o'clock. The details are in the Government Data Science Slack workspace. It's for public sector people. Get in touch with me if you want to be on that Slack space, or you want more information, and the Eventbrite link, maybe we could send that out separately. And it's at 12 o'clock. It's a hugely popular reading group, and I feel it complements the data science ethics group that I regularly attend, because they're reading a book, but we read kind of like journal. I'm never prepared for that, and I'm still very welcome for the Bristol Ethics Club. So there's a lot of interesting things going on for people. So please do join in, and thank you so much for your talk, Hugh.
Yeah, no, thank you very much for having me. Yeah, but just on that note, like the Data Ethics Club, like we've run out of Bristol University, but literally anyone's welcome. I joined when I knew very little about data science and wanted to learn more and get more involved. So if whether or not you're academically inclined or not, we do our best to make sure that everyone's welcome. So we're always happy to have new members. We've got an email list, so you can have a look at that. But yeah, thank you very much for having me. If you have any questions, feel free to ask. But
thank you, Hugh. That's I really enjoyed that, and we have a couple of comments. We've got a few. Thanks, Hugh, and I won't share my screen, but I'm not lying. I am reading. Really interesting and engaging presentation. Learned a lot. Thank you so much. Brilliant presentation. Thanks, Hugh. So I think you've hit the mark, Hugh. We were right. People were interested.
Good stuff.
And I think there's lots of things we can share after. So the things you mentioned, Zoe, the things you mentioned, Hugh, just to get people engaged. And I think one of the points is you don't need to be well versed. You don't need to do all your homework. You can just come to some of these things and just learn more about them. Don't be afraid just to get your foot through the door. Okay, well I'll just go on to do one or two more finishy offy things. So I will just share my screen again while I do that, just to prompt me. Then we can see some of the comments that people have made, so I wasn't making them up. And I'll just move on to my next slide. So I've just got a reminder. It's not a word, is it? It's definitely not. So the Health and Care Analytics Conference, we have actually sold out of in-person tickets. I think there's a waiting list if that would be your preference. But online, of course, is still available to you. So please do get involved. And if you're incredibly disappointed that you haven't got an in-person ticket, we've got 2 more years. So you'll have to get in there a bit earlier next year to get your top seats. Now we've got coming up. I've only got the next 2 huddles coming up here, but there's quite a lot more planned in the next few months. I didn't want to get you too excited about everything that's coming up. So we still are welcoming at some point, not necessarily the next time, Chris Bealey and Zoe Turner to talk more about the data science team, which they have established and are developing within the strategy unit. Onwards and upwards to that team. Very exciting things happening there. And but very soon, in I think the next huddle actually, we have multi-criteria decision analysis in healthcare devices. So strongly recommend you come to that one. And of course, we always have training opportunities for you, and the new prospectus will be out soon. We're just waiting to cross the T's and dot the I's. I do sometimes get that wrong on a few of the training courses. They have already started, of course, as well. But if you go to the website, you'll see what's up there already. And then we've got some which you don't know about in terms of the dates, and that will be available on the website. So I will stop sharing, and I will say thank you again to Hugh. You good luck with your thesis. Good luck with your data scientist role at Bristol University. You're welcome back anytime. Thank you, Zoe, for the intro. Nice one. And I will close there, and I'll see everybody else in a couple of weeks. Thank you. Thank you and goodbye.